This video is brought to you by mywayteaching.com.
In this part, let us solve a very simple problem. The problem statement is given here. If 10 raised to 9 electrons move out of a body to another body every second, then how much time is required to get a total charge of 1 coulomb on the other body? So which means here one body to another body, the charges are moving, and here they're asking how much time is required to move 1 coulomb of charge from this body to this body. So this is the question. Now let us find solution for this question. Okay. See, in 1 second, 10 raised to 9 electrons move out of the body. So it is given in the question, isn't it? In 1 second, 10 raised to 9 electrons move out of the body. So, the charge given out in 1 second, we know the charge, it is given by 1.6 into 10 raised to minus 90 into 10 raised to 9 electrons. So, the charge is 1.6 into 10 raised to minus 10 coulomb. So the time required to accumulate a charge of 1 coulomb, we can estimate that as 1 coulomb divided by 1.6 into 10 raised to minus 10 coulomb per second, which gives the value as 6.25 into 10 raised to 9 seconds divided by 365 years in each day, 24 hours and 3600. This is the total time of the year. So that is equal to 198 years. So to collect a charge of 1 coulomb from a body from which 10 raised to 9 electrons move out every second, approximately we need 200 years. So 1 coulomb is therefore a very large unit for many practical purposes. And even it is very, important to know the number of electrons contained in 1 cubic centimeter of a material, isn't it? So, a cubic piece of copper of side 1 centimeter, it contains 2.5 into 10 raised to 24 electrons, okay? Now let us see another one simple example. How much positive and negative charge is there in a cup of water? So in order to solve this, you just assume the mass of 1 cup of water as 250 gram. Okay. And the molecular mass of water, we all know it. It is 18 gram. And the number of molecules in 1 cup of water, we can calculate it as 250 by 18 into 6.02 into 10 raised to 23. Each molecule of water contains 2 hydrogen atoms and 1 oxygen atoms, isn't it? That is 10 electrons and 10 protons, and hence a total positive and total negative charge. Yes, it has the same magnitude, and that is equal to 250 by 18 into 6.02 10 raised to 23 into 10. The charge is 1.6 into 10 raised to minus 13, which is equal to 1.34 into 10 raised to 7 coulomb. Okay. Now let us see what is Coulomb's law. See, this Coulomb's law, it is a quantitative statement about the force between 2 point charges. It mainly describes the force between 2 point charges. When the linear size of charged bodies are much smaller than the distance separating them, which means if you consider the size of the charged bodies, are much smaller than the distance separating the 2 charges. Okay. The size, even that size may be ignored, and the charged bodies, we treat them as point charges. And the scientist Coulomb, he measured the force between 2 point charges and found that it varied inversely as the square of the distance between the point charges, and it was directly proportional to the product of the magnitude of the 2 charges and acted along the line joining the 2 charges. Which means, in order to understand this statement, let us consider 2 point charges Q1 and Q2 be the 2 point charges. Okay. And R is the distance between them. And the magnitude of the force between them is given by F is equal to K Q1 into Q2 by R square. So, this is the Coulomb's law. Now the question arises, how did Coulomb arrive at this law from his experiments? How he found this? You know, the Coulomb, he used a torsion balance for measuring the force between 2 charged bodies. And that metallic spheres, he measured the charge between 2 metallic spheres. And when the separation between 2 spheres is much larger than the radius of that each sphere, which means the size of the each sphere, the charged spheres may be regarded as point charges. However, the charges on these spheres were unknown. See, it was very Coulomb, he taught in a very simple way. Suppose the charge on the metallic sphere is Q. He considered two metallic spheres, isn't it? So if charge on the metallic sphere is Q, if the sphere is put in contact with an identical uncharged sphere, like this, two uncharged spheres, the charge will spread over the two spheres. Obviously, the charge will distribute to this also. And by symmetry, the charge on each sphere will be how much? Yes, it will be Q by 2. Repeating, again if you repeat the same process, we get the charges of Q by 2, Q by 4. It continues. And now what Coulomb did, he varied the distance for a fixed pair of charges and he measured the force for different distances. And then he varied the charges in pairs, keeping the distance fixed. So once he fixed the distance, once he fixed the charges. So comparing forces for different pairs of charges at different distances, he got the equation, that is F is equal to K Q1 Q2 by R square. So this Coulomb's law, a simple mathematical statement, it was initially experimentally arrived at in the manner which is described now, just now what I described, how he taught. But actual original experiments established at a macroscopic scale, it has also been established down to subatomic level. Subatomic level means where R will be in the range of 10 raised to minus 10 meters. And the Coulomb, he discovered this law without knowing the explicit magnitude of the charge. And now we can use this law to furnish a definition for unit of charge. So in this equation, we find an arbitrary constant, that is K, isn't it? This is an arbitrary constant. And we can choose this K to be any positive value. Okay. And the choice of K determines the size of the unit charge. And in SI unit, the value of K is somewhere 9 into 10 raised to 9. The unit of charge that results from this choice is called as a Coulomb. So if you put Q1 is equal to Q2 is equal to 1 Coulomb, R is equal to 1 meter in the equation, then we get F is equal to 9 into 10 raised to 9 Newton. What is the meaning of this? Which means 1 Coulomb is the charge that when placed at a distance of 1 meter from another charge of the same magnitude in vacuum experiences an electrical force of repulsion of magnitude 9 into 10 raised to 9 Newton. Okay. 1 Coulomb is too big a unit to be used. And we use smaller units like millicoulomb, microcoulomb. And the constant, this K, okay, which we use in this equation, that is equal to 1 by 4 pi epsilon naught. Okay. So we can write the Coulomb's law in another way. First, this is the Coulomb's law. Now we got the value of K. So after substituting the value of K, Okay. And here this epsilon naught, it is called as permittivity of free space. And the value is given by 8.854 into 10 raised to minus 12 Coulomb square Newton raised to minus 1 per meter square. Okay.